Hello everyone, and welcome back to another MCAT ACE lecture. In today's lecture series, we are going to be continuing the work that we put in on the carboxylic acid and derivatives series. So this is a part 2. We will finish everything in this part. If you have not seen part 1, I would encourage you to go back and watch the carboxylic acids and their derivatives part 1, or the initial one, and then you can continue forward with this. So this is the same exact format we were using last time. We've already talked about carboxylic acid acidity, and we have talked about creating carboxylic acids and some of their reactions. Specifically, we have talked about carboxylic acids with acid chlorides and anhydrides, and what we're really going to focus on in this lecture is the reactions involving esters, because they are a bit different than the acid chlorides and the anhydrides. And then finally, we will talk about amides briefly before we get ready to wrap up and do our practice and summary. So when we take a look at the carboxylic acid derivatives, just as a brief reminder, we've got acid chloride at the top. That's the most reactive of the derivatives. Then you have anhydrides, then esters, and then amides. And we discussed this reactivity and the fact that it was based on the ability for a group to leave. So acid chlorides, for instance, were at the top of the list because chlorines make such fantastic leaving groups. Now, we are at this point at esters, and esters have an OR, where R would be an alkyl group for the leaving group. So that leaving group, as we discussed last time, is not going to be as potent as something like a chlorine or the carboxylate ion that would be resonance stabilized in solution. Those are very weak bases and therefore good leaving groups. When we take a look at an ester, the alkoxide, which is going to be the leaving group, that would be the conjugate base that we have in solution there, that's going to be a relatively strong base. Again, the term is relative here. Amides are going to give even stronger, but certainly strong enough that it sort of knocks down the ranking as far as the reactivity is concerned. All right, so the first major reaction that we're going to take a look at here is the Fischer esterification and / ester hydrolysis. So why are we bringing both of these up at once? Well, these are really the same reaction, except they are reversible. So the Fischer esterification takes a carboxylic acid and creates an ester out of it, whereas the ester hydrolysis is going to take an ester and revert it back to a carboxylic acid. Now, both of these are possible with an acidic catalyst, but because the entire reaction, no matter which way you're looking at it, is reversible, they are mirror images of one another mechanistically speaking. So when we look at the mechanism, these are really going to be just reverse pathways, and so they're good to look at together so that we're not really drawing it out 2 times, because that's what we would be doing, is looking at it in reverse. So what we'll do here is we'll show the Fischer esterification, and then we will talk about how the reverse of that, once we have that up here, is going to be the ester hydrolysis. So remember that when we are talking about an ester, the general format for an ester is going to be R C double bond O O R. Now with the Fischer esterification, we are going to use a carboxylic acid to start with. So it's the process of taking a carboxylic acid and converting the carboxylic acid over to an ester. So we're going to start with our carboxylic acid functionality. Okay, now some people will ask about, why don't you use a base here instead of acid? And the problem with using a base is that carboxylic acids are acidic by nature. So you're going to get an acid-base reaction instead of this reversible reaction that we're looking at here. All right, now, what I need, and we'll switch the color for this, I'm going to need an alcohol in order to create the ester. All right. So right here in red, we're going to use ROH, and that will be our alcohol. And then we will also go ahead and add the acid here. Now this is very similar to an acetyl type of reaction. So if you remember acetyl and hemiacetyls from when we discussed ketones and aldehydes, this setup, an alcohol with acidic conditions that's reversible, if you had a ketone or an aldehyde, it would be performing an acetyl reaction. Now we have a carboxylic acid, which has got different functionality than aldehydes and ketones, which we discussed in the last lesson. That's sort of why it's got its own chapter. We're covering it in a different light here. All right, now what's going to end up happening is that we will keep the carboxylic acid portionality minus the OH, so that group right there. And then what's going to take its place, again, switching the color so we can keep track of everything here, is that we will then have the OR from the alcohol over here. All right, and then you have your ester. So how does this work from a mechanism standpoint? And this reaction, again, similar to the acetyl reaction, is very important to know for MCAT students if you come across Fischer esterification and the general process of hydrolysis. You want to understand both of these types of reactions. So to get started, we're going to have the carbonyl group coming and picking out one of the acidic hydrogens. So what we essentially do is we activate the carbonyl complex. We make it more reactive towards an incoming group. And when we do that, we're going to see the RC double bond, and then this becomes OH. That OH has a plus charge associated with it, and then we still have the OH down here for right now. Okay, so that's the first step. Now, right on the heels of that is going to be the ROH that's going to come in, and that is going to attack the activated carbonyl complex. So this guy right here is going to take the pi electrons in order to satisfy the OH, and what we come down to, once we're done with that step, is that we've brought the alcohol along, and the alcohol has brought the proton with it. So we're going to get ready to do a proton transfer in order to continue this reaction. Again, a lot of similarities here between the hemiacetyl formation and what we're doing right now. Okay, so here's the two OH groups, and then what just attacked. So let's keep in red so we can follow along with our alcohol here. Oops. We've got the alcohol that came in. It's got an ROH. And now the formal charge that was originally on the alcohol up here has been transferred to this oxygen, which has given up a set of electrons in order to come in as the nucleophile. So this is the intermediate that we would be looking at here, right? Now, we have electrons that are going to go from the hydrogen attached to that alcohol over to the oxygen. And this is the proton transfer step. So what we're going to deal with here is we're going to say, all right, these electrons go back to this oxygen. And then usually you could actually draw the OH picking it up in solution. But most of the time this is represented by people putting H plus transfer, or you might even see it written out as proton transfer. All right, so what's going to happen after that? We've got the RCOH. Now the transfer has occurred to one of these two alcohols. It doesn't matter which one you pick out because they're symmetrical. There would be no difference. However, what I'm going to select is this one right here, and that's just for the sake of keeping the mechanism clean. It'll be easier to follow. Okay, and then we still have the OR group down there. Now the OR group at this point no longer has the proton. It was transferred over to the alcohol functionality. So now we've got that ether type of format down there, which is going to eventually become our ester in the final product. So continuing forward with this, we're now going to have water leave as it usually would. We'll take the electrons with it. Okay, and then in order to prevent a carbocation from building up, or really in assistance with, it would be a resonance form, you're going to end up moving pi electrons back down. So you're going back to that activated carbonyl type of complex. So what we end up with here, okay, is we've now got R, you've got C, the double bond O has the H, similar to how we started. And we now have the OR group. So we're real close to the ester at this point. This is what we would have right here. Okay? Now, at the very end, you can show water coming to pick this up. You can just show it leaving into solution since we've created acidic conditions. The hydrogen here will give electrons back to this carbonyl, to the oxygen on this carbonyl, and go back into solution. So this is the generation of H+. Now this is important because this H plus here is catalytic. Okay, so when we have a catalyst by definition needs to regenerate itself. It should not be one of the reagents consumed in a reaction. It simply participates in terms of the energetics and lowering the energy of activation to get the reaction started. So we finish this off here, and there we are. Okay, so we end up with our ester. Now, hopefully, the reason I brought this up in terms of the ester hydrolysis, what you can see here is that because all of these steps are reversible, the exact opposite can occur. Because now what I have is I have generated water in this step down here, right? Water has been removed into solution. And so if I have water and H plus in solution, I really have an aqueous acidic environment. So there's no reason that I couldn't reverse each of these steps. So look at the step right here. I'm going to write this in blue so that you can see the reversibility here. All right, so we won't walk through all of it. Hopefully you can follow along. But the first step, so this is for the ester hydrolysis, okay? The first step would be for the carbonyl to pick this up, right? And then I would go back to this type of state. So the next step would be that I would need H2O to come in as a nucleophile and open this up. And then once that's there, I would have H2O here, right? That just added. I would have the OH and I would have the OR from the ester. And a proton transfer is going to occur from the water to the ester. So here's the H plus transfer that's occurring. So now the alcohol has transferred the proton to this ether portionality that is now an alcohol. This would leave, and then we would just finish it up the same way up here that we were looking at before, which is that then H plus could go back in, oops, that's the wrong direction. H plus could go back into solution and regenerate itself because of the catalyst. All right, so I know that's kind of messy. That's why I wanted to do that as the last portion, because we're really showing two different mechanisms going on in here. I really walked through the Fischer esterification in great detail, and the hydrolysis, because we already have a general understanding of how this works, kind of got added on at the end, and I showed those in the blue arrows there. Okay, Fischer esterification, which is a carboxylic acid to an ester, and then ester hydrolysis, which is taking an ester and bringing it back to a carboxylic acid. Reversible, two sides of the same coin, mechanistically speaking. All right, now, there is another way that we can create carboxylic acids from esters, and that is a process known as saponification. Now, saponification is commonly discussed because it's utilized in soap making. That's where the name comes from. So saponification uses base conditions instead of acidic conditions initially. You do need some acid at the end, and we'll show why. But it uses base conditions in order to create basically carboxylate soaps, and then those carboxylate ions can be protonated with the acid. So what I'm going to do, pause this if you need to copy anything down or look at it. I'm going to clear the board, and I'm going to bring up a clean slate for the saponification mechanism, and then we'll take a look at that one in detail. Then there's one or two other ester portionalities we want to discuss, but these are the big ones, and then we'll move on to amides. So let me clear this, and then we will take a look at saponification. Okay, so what I've brought up here is an empty space where we can look at the process of saponification, which again is synonymous with soap making. Now, when we take a look at saponification of esters, you're going to take an ester, and you are going to expose it to a base. And typically this is a hydroxide base, so potassium hydroxide, sodium hydroxide, but any source of minus OH is usually what tends to be utilized in this type of method here, because you're looking to get the carboxylic acid derivative back. So when you start with this, you're going to start with an ester, because it's saponification of esters. You need an ester functionality. And then once you have the ester group, it's going to occur in two steps. The first step is going to be the base, so minus OH. And then the second step is going to be H3O+. All right? Now, technically, even though I'm not going to show it in this mechanism, the first portion so in other words, step 1 here with the hydroxide, the first portion of this mechanism is reversible because you're really exchanging OR for OH groups, and from a pKa level, they are very, very close to one another. So it's difficult to say which one's going to predominate in solution to a large extent because their pKa gap is so narrow. It's less than 1 usually compared to one another. So to give you an idea, the pKa of water is roughly 15.7, and methanol would be 16. So you're talking about a very small, narrow range there as far as which one's going to be predominating in solution versus very large gaps, which then it becomes evident which group's going to leave and which is going to stick around. Okay, but after the second step, this is considered a non-reversible reaction. So when you finish up, you will end up with your carboxylic acid, and we will explain why, again, you need the acid in this step here, this step 2. Okay, so we'll end up with something like this. All right, now, you know what? I'm going to make the OH in a different color also, because that was sort of to help keep us on track and follow along so you could see the different portionalities. So let's just we're going to put the OH back there, but we're going to do it in a different color so that we can follow along here. Okay, so here's our hydroxide, so we can follow where that's going. All right, so the first step in this case, because remember, we don't have access to this acid until afterwards. If we did that at the same time as the minus OH, I would just get a neutralization. I would create 2 water molecules in solution. So I only have the OH present, so there is no acidification of the carbonyl group. It's just that the hydroxide is going to have to directly go in and attempt a substitution here. Okay, so we can't have a carbon with 5 bonds. That would break valence rules. So what we're going to take a look at here is something that would look like this. Okay, so here's the OR. And then we've got the OH that's coming down here. All right, so the key to this is that we are looking for the OR group to leave and the O minus portionality there to reform the pi bond. So the way in theory that this is going to work is that you will get your OR group to leave and you will get this to come down. Now the reason I mentioned this is reversible, okay, is that OR and OH are about equal in their tendency to leave in this situation. So it is very possible that it takes some time to get the OH to go on and the OR to leave, okay, when you're working with that. So once you are able to do this in this sort of reversibility step here, you then have R, C double bond O, okay, and then you have OH. Now, the OH came from the base. So a lot of students stop here and they think, oh, I've got my carboxylic acid. Why did I need the acid in step 2? Right? Well, the reason that you need to have acid sitting around is that think about what group just left. Or if you're using excess hydroxide, which is typical here, what's going to happen with hydroxide and OH? So whichever portionality you choose, just realize that what you're going to end up with here is a strong base and a carboxylic acid. So this, without a doubt, is going to deprotonate. And this is no longer a reversible type of situation. Once you've got a strong base and a carboxylic acid, you will create the carboxylate weak base anion and the alcohol weak acid. Okay, so this is where we start to lose some of the reversibility of this reaction here. So I say, okay, I've got C double bond O, okay, and then it's the carboxylate anion that's really going to be present, because all of the excess base, whether it's from the leaving group or excess hydroxide that's present, is going to lead to this type of situation here. So the reason the H3O plus is utilized is because we need to protonate this carboxylate if we're really looking to get to a carboxylic acid at the end. So when you're working with this, okay, you've got the H3O plus, and if you're interested in getting the carboxylic acid functionality back, you're going to need to take a lone pair and grab one of these protons. And then we can get up to this portionality here, right? Where, just for the sake of the color, we're going to show that this oxygen is from the hydroxide. Okay, so that is saponification. It is the process of using a strong base to act as a nucleophile, kick the ester portionality off, that OR alkoxide group, and then once you've done that, you're going to end up with the salt form, or the carboxylate form. And so if you're looking for the carboxylic acid, you would need to protonate that using acid in a separate step. Now again, a separate step because obviously the acid is going to kill off any hydroxide that would be present in solution there. Okay, so that's saponification. There are a couple other just reactions I wanted to mention briefly. We're not really going to go into a huge amount of detail of the mechanism because we've either discussed the mechanism before or it's not very common to look at the mechanism for them. So let me bring up some of the other ester reactions that it would be important or a good idea to know, and then we will continue forward from there to take a look at amides. So let me clear the board here. All right, so what I've brought up here is an area where we can take a look at some additional ester reactions. So one of the reactions that we know esters can undergo, along with carboxylic acids and a lot of the derivatives, is reduction. So an ester is readily reduced using a strong reducing agent, such as lithium aluminum hydride. NaBH4 is typically considered too weak in order to do esters, or it would certainly be too slow. So lithium aluminum hydride, this is a ×2 equivalence, similar to the acid chloride, followed up with H3O+, is going to give us a primary alcohol. And that's expected. That's what most of the reductions are going to do. If we have aldehydes, carboxylic acids, esters, ketones turn into secondary alcohols, but an alcohol is the general product that we recover when we do reductions. Now, there's an interesting reagent, one that we haven't come across yet, and it is typically associated with or utilized with esters, and it will selectively reduce the ester down to an aldehyde instead of all the way down to an alcohol. Now, when you use this, the reagent that's required is diba, all right? And diba is an aluminum hydride, similar to lithium aluminum hydride. However, it limits the amount of hydrides available because it places diisobutyl groups in place of some of those hydrides. Now, what does this do? First of all, it's a larger reducing agent, sterically speaking, all right? And then second, it's limiting the number of hydrides that are available. This is typically run at low temperatures because you still want to control how fast you are reducing, because reductions tend to go very rapidly if you have a decent source of hydrides. All right, so diba at cold temperatures, I typically see -78 in literature and things like that I've come across, but you should see a relatively cold temperature. And sorry, I've left that out here. This is -78. 78 degrees Celsius would be too warm. So -78, okay? And then you can follow it up with your acid like you would in most cases. Now, if you do that, what you end up with is an aldehyde instead of an alcohol because of the limited reactivity of diba. And just another side note, some people see this as dibol with an L instead of an H. You're discussing or utilizing the same reagent there. The diisobutyl aluminum, whether it's aluminum hydride or aluminum in the name, that's the reducing agent that you're going for here. All right. Now, what's unique about this is that most, as we just said, most of the reduction reactions are these runaway reduction reactions that are going to take it all the way down to an alcohol. That's what we typically expect from reductions. This is a way to selectively produce aldehydes instead of alcohols, if I would like to stop it part way. So if you remember when we talked about the acid chloride in the first lecture, we stated that an aldehyde was sort of the intermediate or the go-to in between, but aldehydes very readily reduce further down into alcohols. And so we didn't have a way of stopping the acid chloride at one equivalence and getting it to sort of stay there at an aldehyde. Well, with DIBA, you are able to do that with esters. All right? Now, DIBA can be used outside of esters, so it can still be used to reduce, for instance, aldehydes and ketones down to their alcohol forms. So it's a legitimate reducing agent. However, you should realize that it's usually not utilized when you have sodium borohydride or some other effective reagent like that. DIBA is usually reserved, at least in theory, for most cases, for the case of esters going to aldehydes when you want to selectively do that. So kind of neat because it will keep your carbonyl intact and preserved there. Okay? So, one of the other things that we do want to mention here for esters, and I'm going to go into a little bit of the theory about this, all right? Because we did talk about it with the acid chlorides. When you have an ester, esters can undergo Grignards. So if I have an ester functionality, the ester can accept a Grignard reagent as a nucleophile, and it will kick off the OR group, okay? Now, some people, a lot of students will ask me, why is this not reversible, right? Because a lot of times when we were looking at some of the other reactions, for instance, the Fischer esterification or the saponification, we had some reversible conditions when we were trying to kick the OR off into solution. So if we take a look at this, we would expect the CH3 to come in, and by the way, this is a 2 times equivalence, and we've got this group coming off here, okay? Now this is a one-way path when we do this. So you get the CO minus, and then you've got the OR, and then you have the CH3, or whatever your group is that came in from the Grignard here, right? Now, what a lot of students ask me is, well, how come you don't have a reversible step here where the CH3 could come back off and the OR would stay on, similar to that first step of the saponification? And the answer to that, so that you can understand it, is that you're looking at what is in solution. So in solution, if I kick CH3 back off, I've got CH3 minus, and for OR, okay, I've got OR minus. So these are the two groups that would be here, right? It's the methyl ion versus the alkoxide ion. So here's what you want to do. You want to look at the acidity or the conjugate, okay, of these bases, which I would have CH4, and let's just say that this is methanol, okay, for the sake of this debate right here, but whatever this R group is, I'm just picking out methanol because it's an easy pKa that I know. So the pKa of methanol and of a lot of alcohols of similar size is going to be approximately 16. The pKa of methane, or the methyl group, is going to be somewhere around 55. All right? So remember, the lower the number, the stronger the acid is, because this is on an inverse logarithmic scale. So we're talking about trillions upon trillions upon trillions of times more acidic, the methanol, versus the CH4. Well, what do we know about conjugate acid-base systems? We know that if this is strong, as far as an acid is concerned, and this is weak, and again, these are relative terms. An alcohol, methanol, is not a strong acid. In fact, it's amphoteric. It can be an acid or a base. But when we take a look at methanol, all right, this is strong relative to methane. Methane has a pKa of 55. So we're going to call methane weak, and we're going to call methanol strong in this situation that we're looking at here. So what does that mean about the conjugates right here? Well, it means that in that case, the OR is going to be a weak base in comparison to the CH3 minus, which is going to be a very strong base, okay? And so what do we know about leaving groups? Because we were debating whether the CH3 would leave or the OR would leave. That's what we're discussing here. Well, we know that weak bases tend to make better leaving groups. So is OR a weak base? Relatively speaking, no, it is not. But in comparison to the alternative, to the methane conjugate, you are going to deal with a very weak base in comparison. And so therefore, the OR is guaranteed to leave in the case of the ester when you're undergoing a Grignard reaction relative to whatever R group, in this case methyl, that you're sending in with your Grignard reagent. So that is why there is no reversibility associated with this. There is also no reversibility with the hydride reactions that we just took a look at, because H minus, the conjugate of H minus is H2, and for that the pKa is approximately 35 if I'm not mistaken. All right, and so again, 35 compared to 16, you are not in a close enough region, whereas something like minus OR and minus OH, okay, because this came from H2O, and H2O has a pKa of 15.7. So let's compare water's pKa to methanol. They're almost identical. So now the debate as to which one is going to be the better leaving group, aka which one is the weaker base, that is within less than 1 pKa unit. So you've got to allow for some time, some equilibrium, some reversibility in that case, versus one that's very straightforward and one-sided like this. Okay, so I know that was sort of a little tangent there, but it's very important to understand why in some cases OR groups will leave, and then in other cases they will not leave. So for instance, just a regular type of SN2 reaction, OR groups are very strong bases. They're not usually going to leave on their own in a case like that in exchange for, let's say, a chlorine or something else like that. Okay, so now that we have that out of the way, continuing forward, right, we would bring this down, and what we end up with here would be a ketone. So this is similar to what we saw with the acid chlorides in the first lecture. So now I've got this CH3 here, right? So because this is a × reaction, I'm going to expect the Grignard to do the same sort of behavior again. And what I'm going to finish up with, right, the final product is going to be R, C double bond O, and then, I'm sorry, not C double bond O. That's my mistake. It's going to be a tertiary alcohol. Okay. So CH3, CH3. All right, so that would be the tertiary alcohol that would result in this case. So esters can undergo double Grignards just like the acid chlorides, probably not as fast or as readily, although they're still going to undergo Grignard reactions very fast because this is not a reversible reaction. But it's similar, mechanistically speaking, to the acid chloride reaction, and you can get tertiary alcohols out of that. All right, so that covers the ester reactions I really wanted to mention. Other organometallic reagents, as I mentioned in the first lecture with acid chlorides, such as Gilman reagents and things like that, are applicable to esters. You can utilize other organometallic reagents. Again, Grignard is probably the most common one you're going to come across, whether it be on the MCAT or on any sort of undergraduate textbook or exam. That's one of the ones that's most common. So I'm going to clear off the Grignard portionality here, and we are going to get ready to talk about the amides very briefly. We're not really even going to go over the mechanism for it because they are, relatively speaking, they're non-reactive, but there is 1 or 2 points I wanted to bring up about amides, okay? And then we will get ready for our practice session, and then finally summarize and sum everything up. So let me clear the board here, and we'll discuss amides. All right, so let's briefly discuss amides here. One of the major things that we're going to find amides with, outside of a biochemistry lecture where we start to talk about peptides and, amino acid chains and things like that, amides in general are the least reactive of the carboxylic acid derivatives. They're pretty stable overall. And when we take a look at that, one of the big reasons is because the leaving group, if I were to get an amide to undergo a nucleophilic addition, would be this amide anion, and the leaving group there is a very, very strong base. So we're not going to expect it to leave into solution very readily. It's going to be reactive and come back in. All right, now one of the reactions that amides can undergo, one of the few ones, is hydrolysis. So you can get a general form of an amide, and I'm sticking with the NH2 form here, but you could put alkyl groups on your nitrogen as well. all right, meaning that this could be an R group instead of an H if you wanted there. But what you're going to end up doing is you're going to set up reversible conditions except for the very last portionality, kind of similar to the saponification. All right, so this can be H3O+, typically it is, and heat, or not in the same reaction, or using a different method, you could do it with base catalyzed. You can do that as well, similar to the saponification. Okay? So what you end up with is you're going to get the R, C double bond O, OH, so you'll get the carboxylic acid back out of that in order to basically undergo hydrolysis with an amide. However, I said reversible up until the last step, and that is because if you think about it, once we have the amine that would correspond to the amide, so in other words, once I have NH3, let's say, okay, plus I've got a carboxylic acid, the reason that this cannot completely reverse is because this would undergo an acid-base reaction, all right? It turns out that when we had esters, the acidity of an alcohol is not, the basicity of an alcohol is not as basic as an NH3. This group right here is a very decent base. And so therefore, I'm going to expect an acid-base reaction here versus any sort of nucleophilic attack of the amine back in order to create the amide. So in other words, this will be reversible in all of its steps up through the last one, but we really cannot take a carboxylic acid plus any type of amine and expect that we're going to go back towards the amide section. So how do we create amides? You typically use an acid chloride, and then you will end up submitting whatever amine you want, and you will get the corresponding amide. And if you have any questions about that, you can look back at the first lecture we did, which dealt with the acid chloride derivatives. All right, so that's really the main things about amides. You need to understand their lack of reactivity and their high stability comes from the fact that the NH2 group is not going to leave very readily. It's not going to make a decent leaving group. And then on top of that, the one reaction we really can get out of amides is we can turn them back into carboxylic acids. Again, the conditions here are probably going to be more severe. You're definitely going to need some more heating than you would with esters or something like that. But it is possible. The mechanism here is going to be very similar to the mechanism you would expect with the ester. So the Fischer esterification, amide hydrolysis is going to be similar in terms of the process that we saw in that case. Okay, so when we are considering this type of reaction, just know it's going to be very slow and reversible, and typically the amide functionality is not going to be very reactive to many other functional groups when we start looking at them in comparison to something like an acid chloride. All right, so that should cover what we really wanted to look at. We're down to amides here on our list. So what I'm going to do is I'm going to bring up the questions at this point. So we'll have several multiple choice questions just to test your knowledge and get a decent understanding of where you stand with this. A brief reminder here, I do want to remind people that when you take a look at the practice problems that we associate with the MCAT ACE program, so outside of the videos, okay, I give you some basic questions here to make sure you are following along and understanding. You might go to the MCAT practice questions that we offer and you go, wow, these are really hard in comparison. And again, I've reminded you on several other videos, the reason for that is that we really want your training to be complete before you step out and go forward to taking the MCAT. We want you to have seen everything. So this is your lecture, your in-class portionality here, right? Then you practice yourself, you find as many questions as you can test yourself on, and we just wanted to make sure everybody's aware of any of that sort of discrepancy you might come across and go, well, why weren't these questions this hard? It's because this is basically where you're gathering your material, and then we really want to go in depth and apply your knowledge when you're preparing for the MCAT. So enough about that. I'm going to clear the board and I will bring up some questions, and we will make sure that everybody is set here as far as carboxylic acids and their derivatives go. All right, everyone, so I have brought the questions up here. There's going to be a total of 6, and this is going to encompass the material from the previous lecture and the lecture that you're looking at right now. So keep in mind, this is all carboxylic acid and carboxylic acid derivatives. So therefore, all of these questions are going to fall under that content. So there is some stuff in the questions here that relates back to the initial previous video, because this was a two-part series. So, number one, which set of reagents will produce the desired product? You can see the reaction on the right. You have an acid chloride, it's going over to a primary alcohol. You need to pick out the set of reagents that would do that most effectively there. Okay, now, number two, which of the following can explain the order of carboxylic acid reactivity? Couple of choices there. Number three, which group would modify benzoic acid to make it more acidic than its current state? So in other words, I've shown you benzoic acid over on the right there. Which of these groups, if I add them to the benzoic acid, the amine, the alcohol, the methyl, or the cyano, the nitrile group, will enhance or increase the acidity of the benzoic acid functionality? Number four, a carboxylic acid can be directly converted to each of the carboxylic acid derivatives except for, and you have all the derivatives there. So there's one of the four derivatives that I cannot directly obtain from carboxylic acids. So that's what the question is asking there. Which set of organic reactions are in equilibrium with one another at all times? Saponification and ester hydrolysis, Fischer esterification and saponification, ester hydrolysis and Fischer esterification, reduction of esters using Diba, and oxidation of aldehydes. Those are the options there. And then finally, to really test your skills here, number six, which pathway could create an aldehyde from a carboxylic acid? So that is to state, you start with a carboxylic acid, your end goal is an aldehyde, that's your product. So pick out any carboxylic acid, I would make it simple, draw it on a piece of paper, apply these reagents, and see what you would come up with. What would you end up with as your product? There is one correct answer out of this bunch. So those are the questions. I will scroll through them one more time. Take a chance to pause where you need to, if you need to copy anything down. Okay? And again, as always, the goal here is that you should pause the lecture. You should work on these yourself, and then we will go through and work on these together. So I encourage you, after you've put in your full effort, to unpause the series and to allow it to go through all the answers with you. All right, so those are your questions. Good luck with them. Go ahead and get started, and then unpause the video when you're ready, and we will go over these together. All right, so hopefully you had a chance to take a look at all of these, and you also had some notes to go back over and reference as you were looking at this. Now, number one, which set of reagents will produce the desired product? We're going from an acid chloride to a primary alcohol. So the correct answer here should have been, all right, letter A. So when we're working with this, the LAH is really what we're looking for, because that 2 equivalence LAH is going to do a double reduction, and the acid chloride will go down to a primary alcohol. So letter A is correct. What would the others have been? Well, if I went with B, this is a double Grignard, and double Grignards with acid chlorides are going to give tertiary alcohols. This is not a tertiary alcohol, this is the primary alcohol. And if you take a look, it's got 1, 2, 3 carbons. I've got 1, 2, 3 carbons right here. So this has been reduced without any additional carbon adding, which is what the Grignard would do. Okay, NaOH and H2O and H3O+, both of those are aqueous conditions that would revert the acid chloride back to a carboxylic acid. So what I likely would have ended up with there is something that looks like this instead. Okay, so A was the correct answer in that set. Number two, which of the following can explain the order of carboxylic acid reactivity? All right, so A, the resonance available to leaving groups. Well, there is something to be said for that, because if I take a look at the anhydride leaving group, it does have resonance stability, right? And that resonance stability is helping to delocalize that charge, making it a better leaving group. So maybe this is possible. I'm going to come back to that, all right? B, the acidity of leaving groups. So let's think of the other leaving groups I have. I have Cl minus, I have minus OR, and I have minus NH2, right? Are any of these acidic? Not really. I would classify these as bases and not as acids. So I would cross out B. All right? C, the basicity of leaving groups. Well, these are all bases. And one of the things that we discussed were that the weaker bases become, the better the leaving group. So that would mean that this right here, which came from HCl, would be the weakest of the bunch. And it turns out the acid chloride is number 1 on the reactivity list. The anhydride is also weak. That's number 2. Then we start to get stronger with the OR. So I think you see where I'm going here. This is most definitely the correct answer out of the bunch here. Okay, and then steric hindrance of the leaving groups. That doesn't make as much sense because if I take a look at my ranking here, I've got this large group from the anhydride, and it is more sterically hindered than something like an NH2. So I would expect to see NH2 higher on the reactivity list if that were the case, right? Because it's not as sterically hindered. Now, does resonance affect this? Yes, because this resonance is allowing this to become what? A weaker base. So it's really the fact that it's a weaker base due to the resonance. Okay, the resonance is kind of an underlying factor. Because if it was only resonance that was explaining the reactivity of the leaving groups, the anhydride would be number 1 because it has resonance. And then all of the other leaving groups would be tied because they don't have resonance. So it's not just a resonance argument, although the resonance is helping to explain the level of basicity. Okay, it's a weak base in that case. So it's very important to distinguish the difference there, which is why we kind of marked that down with a question mark, but we came back and realized that what A is telling us is just something about C. Okay, so C is the correct answer there. All right, which group would modify benzoic acid to make it more acidic than its current state? So if you remember, we went through some examples where we put para-substituted groups on here, right? And so if I put a group on there, it can affect the acidity of benzoic acid. Now, the key here is that we were looking for electron withdrawing groups when we're dealing with the acidity of the benzoic acid, because those, when we have the conjugate, right, it'll be resonance stabilized, but we're also looking to withdraw electrons from the excess electron buildup. And so if you take a look here, NH2 has a lone pair, and so this lone pair through resonance can donate into the ring. Okay, so that's going to be out. Same thing with OH because of its lone pairs. This is a donating group. Okay, a methyl is a weak electron donating group. It's not as strong as those that can donate by resonance, but it's a donating group. So that leaves C and D. Okay, C is certainly weaker. I would select it over A or B. But then what about D? D has a cyano group, right? This carbon does not have any lone pairs if I directly attach it to the ring. And this nitrogen is going to have a strong pulling effect through electronegativity this way, okay? And so I could say through resonance and through induction that this is going to steal electrons from the benzene ring, right? And so this is an electron withdrawing group, and therefore I would expect that the cyano group would enhance the acidity most because it will provide electron withdrawing effects in comparison to any of the other three. Okay, so all three of these two were strong electron donating groups. Okay, so those are definitely out. That's the opposite of what I want. This is a little bit better. It's a weak electron donating group, but it's still going to donate more, which means it's going to enhance the basicity, not the acidity. Whereas the electron withdrawing group, and this would actually be classified as a strong electron withdrawing group, that is going to play the exact effect that I'm looking for. All right, 4. A carboxylic acid can be directly converted to each carboxylic acid derivative except for, okay, so if you take a look at these, the correct answer here would be B. It's an amide, all right? Now, how do I know that? Well, I can take a carboxylic acid over to an ester using the Fischer esterification, which I'm going to abbreviate as Fe there. The acid chloride can be directly obtained using SOCl2. okay, with the pyridine. And while we didn't discuss the anhydrides in detail, we said that they were very similar to acid chlorides in reactivity, and therefore it turns out you can use another carboxylic acid, a carboxylate anion, in order to accomplish that. Okay, so that leaves us with the amide. And we said that if I take a look at carboxylic acids, okay, this was actually in this lecture we discussed this, and I have an amine and I'm attempting to bring the amine over to an amide, okay, I cannot do that because I'll get an acid-base reaction with this acidic proton. So what I would really need to do here is take the carboxylic acid, I would turn it into an acid chloride, and the acid chloride could be converted into an amide. Okay, that's the way we typically get at amides when we are trying to create them, because the acid-base reactivity between these two are not directly compatible. It's very difficult to turn a carboxylic acid directly into an amide. It's better to go through the acid chloride. Okay. Which set of organic reactions are in equilibrium with one another at all times? All right, so let's take a look at these. Saponification and ester hydrolysis. Now, saponification was reversible up until the last step, if you remember, and then after that last step, we did not consider it to be reversible anymore. And if you take a note here, this says with one another at all times. And so saponification is actually very close to the ester hydrolysis, where an ester goes back to a carboxylic acid. However, that last step makes it so that it's not a reversible at all times. Very close, though. Okay, the Fischer esterification and saponification. Well, this one's out because Fischer esterification and saponification are two ways that we can obtain an ester from a carboxylic acid, but they are not reversible reactions of one another. In fact, they're headed in the same direction, one of them using acidic conditions, one of them using basic conditions, but they are not in equilibrium with one another. Okay, ester hydrolysis and Fischer esterification. Yes, this is the correct answer. Okay, reduction of esters using diba and oxidation of aldehydes. When you reduce or oxidize, those are not in equilibrium with one another. Okay, you can reduce and then you can oxidize, and even then, an oxidation of an aldehyde is going to give you a carboxylic acid. Okay, and a reduction of an ester will give you an aldehyde. Those don't go back and forth to the same thing. So in other words, when I oxidize an aldehyde, I don't get an ester back. I get a carboxylic acid. And then aside from that, the fact that they're not giving me the same products back and forth, they are not in equilibrium with one another. Those are one-directional reactions that I have to go back and forth. All right, and then finally, which pathway can create an aldehyde from a carboxylic acid? So we need a general carboxylic acid over here that we're going to work with. Doesn't matter what you picked. Okay, and then we are going to apply these reagents. So I'm going to just abbreviate to keep all the writing to a minimum of structures, but hopefully you can follow along with this. So A, if I apply SOCl2 and pyridine, this becomes an acid chloride. Okay, and then if I use LAH and H3O+, this is going to be reduced down to a primary alcohol. Okay, so that is a fail because we're looking for an aldehyde from a carboxylic acid. Now, I know that it doesn't say two equivalents up here, which I did on purpose because in the other problem it did. I did this on purpose because if you remember when we talked about this, lithium aluminum hydride is not controllable. You cannot say, well, I'll use one equivalence of it and then it'll stop at an aldehyde and I'll be able to control it that way. You cannot do that. So yes, I purposely left out the fact that it was two equivalents in this case because you cannot control those reactions. Okay, so that's important to remember. All right, so let's take a look at B. With B, and I'm going to go through, I'm going to delete these each time just so I have room. Okay, so our answer for the first one was that we would come up with a primary alcohol. So let's just note that so we're keeping track of stuff. Okay, primary alcohol, gone. All right, so for the next one, SOCl2, another acid chloride. In fact, we can state that all of these are going to be acid chloride because if you look at what we start with each time, right, SOCl2 and pyridine. Okay, then CH3OH and pyridine, an alcohol and pyridine with an acid chloride. Hopefully you realize this would give you an ester. Okay, so an ester is not an aldehyde. I go to 3, diba in cold conditions with H3O+, that is going to convert this to an aldehyde because dibo will selectively reduce, okay? And that will give me the aldehyde that I'm looking for. So B would be the correct answer here. Now let's just look at the other two so we understand where they went wrong. Okay, acid chloride using SOCl2, and then ester. After that, we used LaH and H3O+. This is the same problem as the first one. I cannot selectively control this. It's going to take the ester to a primary alcohol. I cannot assume that I'll stop at an aldehyde using one equivalence. Okay, and then finally, what do we have in this last one here? Acid chloride, ester, okay, and then OH with an ester and H3O+. What does that look like? Well, that is saponification right there, if I had an ester. And when I use saponification on an ester, I go back to a carboxylic acid. So that was probably the most useless of all of them, because what I did was I started with a carboxylic acid, I ran through my set of reagents, and I ended up with a carboxylic acid. So D would certainly be out. There was no use in that. And A and C would give primary alcohols. They would not give aldehydes because they were not selective reductions. I couldn't control them. All right, so hopefully this was able to sort of stretch your brain a little bit, get you thinking about the things that we learned here. So I will pause the video at this point. I will bring up the summary so that we can wrap up, and then we will see you guys for future lectures. So let me just bring up the summary here real quick, and we'll get started with that. All right, everybody, so here's the summary. For carboxylic acids, when we initially started talking about this at the first lecture, we mentioned that carboxylic acids get their functionality due to resonance. So the reason that the OH group is acidic in comparison to something like an alcohol is the fact that there is resonance available there. All right, now we also talked about electron withdrawing groups. We saw this in the problems that we just practiced, and we also discussed it in greater detail during the first lecture. Electron withdrawing groups do not cause acidity for carboxylic acids. They enhance the acidity. So I can take a carboxylic acid and I can put an electron withdrawing group in general proximity towards the carboxylic acid, and that will enhance its acidity, but it is not going to be responsible for the initial acidity or what's creating or making that compound acidic. All right, now, there are multiple ways to create carboxylic acids that we talked about. So we did talk about nitrile hydrolysis, which took cyano groups, and we ended up taking H3O+ and heat. So it was having some sort of group like this, plus H3O+ and heat led to that. We talked about oxidation of primary alcohols, so you can use the strong oxidizing agents, not PCC. We talked about using the chromate reagents, things of that nature. We also talked about alkene and alkyne oxidative cleavage, where you could cleave those double bonds in half. The Grignard carboxylation, which was a CO2, so it was a carbon dioxide plus Grignard reagent, which I'll abbreviate here. And then you follow that up with H3O+. This was a nice one because it led to a huge versatile ability in terms of picking out the type of carboxylic acid that we wanted. And then the opposite of that, as far as very limiting reaction, was the alkyl benzene oxidations, where we took the Friedel-Crafts reaction, we placed some sort of a CH group on the benzene, and then we underwent an oxidation with KMNO4, right? And with KMNO4, there was a condition that we needed alpha hydrogens to be present on that group, and it would always go to just benzoic acid. So there would only be one carboxylic acid for each of the alkyl groups, no matter how long they were on that chain. Okay, so then we started talking about the reactions of carboxylic acids. Therefore, we got into the carboxylic acid derivatives. We talked about acid chlorides. These guys were the most reactive out of the bunch. Because of that, they can create all other derivatives. And remember, we talked about, and again, we discussed this multiple times, it is the strength of the base, or really the weakness of the base, that's leading to the strength of the leaving group, right? So acid chloride could create all the other derivatives, and we also saw the ×2 equivalence. So this was applicable to the Grignard, and it was also applicable to the LaH, where we were doing 2 equivalents in terms of the additions there. Okay, and then again, the other derivatives were usually the corresponding pieces. So you could use amines, you could use alcohols, or you could use carboxylate anions, and you could end up getting your acid chloride to become any of the other derivatives. And H2O or minus OH would turn an acid chloride into a carboxylic acid again. Now remember, acid chlorides were created using SOCl2 and pyridine from a carboxylic acid. Okay? We did discuss anhydrides briefly, and we said they are also reactive. They can create everything in a similar manner to that of acid chlorides, except they cannot create acid chlorides themselves. If you wanted an acid chloride and you had an anhydride, you would need to create a carboxylic acid from the anhydride, and then you would use SOCl2 to convert the carboxylic acid over to the acid chloride. Okay, esters, we talked this lesson about the reversible reactions. So specifically, we had the Fischer esterification and the ester hydrolysis. Those were in equilibrium with one another. And then we also talked about saponification, which was a method which used bases in order to do that. And I do want to bring something up here. A lot of students will ask me, well, what about esters creating amides? Can you do that? And the answer is yes, because amides are lower on the reactivity list. So you can create amides from esters. However, the reason this usually is not discussed in a whole lot of detail is that acid chlorides are far superior in terms of their reactivity and creating amides in better yields than setting up a reversible reaction where you try to do a conversion into amides from an ester. So most of the time, if you're going to do that, you use an acid chloride in order to create an amide. Okay. We did talk about selective reduction being possible here, so we do have the double equivalence just like with everything else. But we also come across and we have the idea that we can use diba to get an aldehyde instead of a primary alcohol. And then finally we wrapped up with amides, and we said that there's a lack of reactivity there. We took a look at the reason why, because of the leaving group. The NH2- would be a very strong base, or any other type of N- group. And then we did mention that they can undergo hydrolysis in a reversible type of scenario up through the very last portion, because then if you tried to reverse it after you had the amine, you would get an acid-base reaction instead of getting the actual amide back. And that was, again, one of the questions that we saw, which was which of the derivatives can the carboxylic acid not directly obtain? And that's the answer for that one. Okay, so hopefully this sums everything up. Please feel free to go back and review, check out anything you need if something in the summary didn't make sense there. Otherwise, that concludes the carboxylic acid and derivatives part 2, and it also concludes carboxylic acids and their derivatives in general. We've now covered what we need to for that portion. So good luck with your studies in terms of carboxylic acids on the MCAT, and we will see everybody for the next lecture series. Thanks a lot.